Hey guys, so I want you to imagine that you had a Rubik's Cube and then you translated the colors on the edges of the squares of that Rubik's Cube into symbols, into some language, okay? And then every possible turn of the Rubik's Cube, you also used a symbol to denote that so that you could basically translate solving a Rubik's Cube into some language that you could write down on paper. So that if I gave you an initial configuration of colors, assuming that it was solvable, one could either solve the Rubik's Cube by hand, right? Or they could write down the solution in terms of this language of symbols that we've made up, which represent like each action that you're doing, each possible twist on the Rubik's Cube. And then I think that this is a very good metaphor for a lot of modern math education, because I feel like modern math education, people have been taught this symbolic language, right, to solve like the Rubik's Cube. But oftentimes you'll see that they just know how to they just know the algorithm, and there's an algorithm to solve a Rubik's Cube, right? They know the algorithm that once, if I give you an initial problem of a certain form, like an initial Rubik's Cube configuration, they know how to go from one step to the next using the symbolic language and then get the answer and solve the Rubik's Cube. But they don't actually know that they're solving a Rubik's Cube. That's the crazy part. They don't actually know that they're solving a Rubik's Cube. They're just doing the symbolic algorithm and steps that they've been taught. And they are solving Rubik's Cube, but they don't realize it. I think this is a much broader metaphor for math education, and also a specific metaphor for row echelon form reduction of a matrix, okay? Finding the RREF of a matrix. So yeah, I mean, if you think about finding the RREF of a matrix, right? A lot of times what you're doing is you're doing these row transformations, and you can do the row transformations in a very specific order. So get a 1 on the first pivot, right? And then get zeros beneath that 1, and then move down to the next pivot and repeat the process, etc. Very algorithmically. And then once you get the REF of a staircase of 1, you get a pivot. All your pivots are 1s and then zeros beneath all the pivots. Then you work backwards from the bottom of the staircase and reduce the matrix into RREF, right? This is just a series of steps where you're just adding rows together and multiplying rows by a constant, maybe switching rows, and you're basically solving. You're basically solving, taking a matrix, getting the RREF. But what you're actually doing is like a very complicated three-dimensional process where, if you think about the problem of AX equals B in terms of matrix math, right? That's saying we know a point in space B and we want to express it in the basis of A, right? And so basically you have the basis, the column vectors of A form some basis for your vector space, and that basis can be used to create the vector B, basically, via some unique linear combination of vectors in that basis. And then what you're doing is you're essentially changing and manipulating that basis in a very specific way, right? In a very specific way, via interchanging two vectors of the basis, scaling one vector of the basis, or moving one vector along the linear span of the other vectors in the basis, right? So adding or subtracting scalar multiples of other vectors in my basis into one of the vectors. And with those three operations alone, those are basically row transformations. So really you're like physically doing something geometrically in a vector space. And then what you're doing is those vectors eventually become solved and become like, you basically get them, you do this series of row transformations, you get them into the standard basis, right? The standard unit vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, etc., right? And then once you have that standard basis of vectors, okay, well then